All right, welcome. So I'm going to speak a little bit about Spotify and how we build our backend services, or build our backend in general, perhaps. Is everyone aware of what Spotify does, approximately at least? We try to be a decent music streaming service. Short background on myself. My name is Niklas Gustavsson. I work in our Gothenburg office. We have a small development office in Gothenburg. I'm a sort of a long-time distributed systems scalability geek, so Spotify is a good fit for my interests. This is sort of a weird place for me. I did some .NET stuff like I think it's more than 10 years ago, but right now it feels like stepping into a completely parallel universe to where I'm normally at. I haven't used a Windows machine for probably a decade or so. But I hear it's great. Is the gag still a thing? Yeah, all right. Good. All right. Please interrupt at any time. I'd love to get questions, and I'll try to answer as many as I can. I mostly work on the back end at Spotify, so if you have very detailed like client or design questions, I might not be able to answer them, but I'll be happy to attempt to. And you're more than welcome to contact me afterwards and with follow-up questions or anything. And if there's anything I can't answer right here, I'll try to look it up afterwards and get back to you. All right. So this talks, the theme of this talk is how we architecture our backend. And this has been the way the Spotify built their backend since the very beginning. I worked there for a little bit more than 3 years. But this has been around for much longer than that, since 2006, basically. And for me, I come from a very like enterprisey type of background. I did consultancy for many years, working at fun companies like Ford or Sony and so on. And the way Spotify builds their stuff is vastly different from what I'm used to. And I think it's now become slightly more popular, and I'm going to come into that. But I hope this will be useful for you, even though we use a completely different tech stack than I think most of you do. And there's been a lot of hype lately about something that is called microservices. And while I've actually never heard that word used at Spotify, it's very much like what we do. So this talk could arguably be called microservices in anger. I'm going to go into how we build stuff and the pros and cons with that and what we do to sort of work around some of the cons. There's been a lot of discussions about what a microservice is, what's the definition of it. Martin Fowler, the link on the slide, has some good discussions around it. I won't go into that at all. I can say that looking at our actual like lines of code per service, it's in the lower thousands usually. I don't know if you would define that as micro or not, but that's the size that we're sort of comfortable with. We do have exceptions though. So the system that manages our playlist, for example, has like 75,000 lines of code. So that's a larger piece of code. So why do we build our systems using these small services? And we can start with trying to contrast it with the exact opposite. Now, this is what I was mostly used to before coming to Spotify. And that is building larger monolithic systems, which you deploy as one large unit. And the problem with this is that it requires a shitload of coordination at basically all levels. You need coordination at your requirement level. What stuff should go into this large piece of software? In what order should we do that? How should we prioritize these? We need to test things. So if I change something here, does that affect something over here, and so on. And the same thing with releases. So you get into all of these release syncing. And Spotify actually have this exact problem as well, because our clients are a large monolith with teams working all over the company to fit features into the clients, and that requires a lot of coordination. So it's not like we're immune from this problem, but at least we are in our backend. So one of the reasons, or I would maybe argue the main reason why we really like this way of doing it is that each and every service that we do becomes really, really simple. It's really easy to argue about what this service does. We attempt to have each service do exactly one task and do it well, instead of trying to mix and match stuff into the same code base. That has many good properties. One of them is that we get more robust code. So it's much easier. When shit hits the fan, and it will always do that, we have a much easier way of reasoning about why this broke and what should we do to fix it. And we limit the blast radius when something goes bad. So if one of our services go bad, and at any given point in time, there will be some services having issues for scalability reasons or whatnot. That will only affect the small part of functionality for our users. So we have one of our classical examples is that the team that I manage, we own a system that keeps track of the number of playlist subscribers. That system, for various reasons, is still pretty much an unstable system. It will fail it every now and then. But that only affects that follower count number in the client. And we can live without that functionality. Everything else in the client will work fine. So that's a good way of limiting your blast radius. If this would have been a larger system and it would have the same type of scalability problems that this subscriber count system has, we would have a much larger piece of functionality that would be broken for the user. Doing one thing and one thing well also means that we don't need to have as much compromises in between different types of features. So if we for example have a system, and I'm going to cover this a little bit further later on, that deals with search suggestions. So when you type in the search box, it will very quickly return a result for maybe this is what you're looking for. First, when we wrote this, we tried to fit that into our general search service, but it turns out that these two systems have very different scalability properties. So the search system must contain our entire catalog. You must be able to search for any of the 25 million or whatever the official number are tracks that we have. You should be able to find any of those in our search system. And you can do all types of complicated searches using Boolean operations and whatnot. The search suggest system can make many other limits to that. We might not need to fit our entire catalog in it. It's fine if the user types in a few letters that we just suggest the most popular content. And maybe we can fill in the additional content from the full search system if we need. But the search suggest system needs to be really, really, really fast. We need to return results within a few milliseconds or so. While the search system can do its work, you have a completely different expectancy from a user point of view when you're typing in something and we actually press enter and is waiting for the search results. We can do very different things. Splitting these into two different systems means we can scale them completely differently. And this is something that we try to do. This is not obvious at all times, of course, how we should partition our functionality, but we try to do it as well as we can and iterate on breaking things apart where it doesn't fit. Yeah, so I already spoke a little bit on scalability with these systems. Again, making smaller systems makes them easier to scale, and I'm going to come back to this a little bit later as well. Basically, this comes down to a very classical piece of Unix philosophy. You've heard of Unix. It's something that lives outside of your range, maybe. There's a book by Eric S. Raymond called The Art of Unix Programming. I strongly recommend anyone to read this. And it has all of these rules about how to build a Unix system. And one of them is rule of modularity. And this piece of text talks a lot about code and how we should have interfaces so we can switch in implementations. And we're all very much aware of this. We use it daily when we write our code. But this is also applicable at the system level or at the service level. And that's exactly what we do. So basically, we have services that have well-defined interfaces, and we can switch out service implementations pretty much at any point. And we do this, I shouldn't say frequently, but we do it every now and then. So when we grow out of a system, we designed a system to scale to a certain number of users, for example. At the point where we grow past that number of users, we might need to replace it. And we've done this. So for example, we're right now looking into building the third iteration of our user service, which might or might not be completely transparent switch from our current user system. It turns out that that system is used by very many services at Spotify. And if we can maintain that API, it will probably be very useful and much easier to switch out. And we've done the same with the playlist system. The playlist is at its 4th generation right now. At some of those generation switches, we've done large migrations. So that's hurtful, of course, because we needed to break backwards compatibility. But we try to do the migration as easy as possible. And having these modularized services makes that far easier than if we had a large system. And at the more organizational level, this enables us to embrace Conway's law. So Conway's law is something that it states that the outcome of your organization will reflect your organization. You can actually, if you know the Spotify organization, you can actually see this fairly easy in our clients, for example. You can see that there's a team that works with search. There's a team that works with playlists. These are different features in the client. We might not want it to look like that, but Conway's law sort of stipulates that we'll end up there whatever we want. At the backend level, we can actually very much be conscious about this and actually embrace Conway's law. So we can have an organization, and we do, that is broken down into large number of autonomous small teams, then each and every team works on a small part of the Spotify functionality. And they can work independently of each other, meaning we don't need to do all this coordination. We don't need to sit in release sync meetings or whatnot. Each squad can build and deploy and operate their services the way they want to do it. And they can use the methodology that they want to use. So some teams will use Kanban, some teams will use Scrum, some teams will use something completely different. It's all up to the team. That also means that we don't have like the architect type of role at Spotify. We do actually have, I think, 2 or 3 people that call themselves architects, but they're not very much involved in the day-to-day work on systems. So basically, each team decide on how they want to build a system. We have a small set of guidelines for how they do that, but basically it's up to the team to do it the way they want. And internally we work in a sort of open source way, so every developer has access to all source code and can work on any system. So if I need a change in some other team's system, I can just make a pull request for that change and have that team merge it and deploy it. So how do we define a service then? I already covered some of this. So basically, we try to make it autonomous. That doesn't mean that it doesn't have any dependencies towards other systems. As I will show soon, it might very well have many dependencies towards other systems. But it's well defined and it works on its own. And we might try to isolate the effects of the dependency it has on other systems, so that if another system goes down or has issues for whatever reason, we try to limit the effects of that. So again, taking this system that counts playlist subscribers into account again, there are services that depends on that, but they know that this system is unreliable at this point, and make sure that they're not completely dependent on it. So they will fall back to showing no subscriber number, or will do something else which makes sense in their domain. Each of these services have well-defined interfaces. Again, this helps with switching out. It helps with the not having that much coordination in between teams. We actually have our own protocol, which is called Hermes, which is built on CRMQ. I'm not sure if you're aware of that. It's an open source product that defines a sort of very lightweight message queuing interface. So we use that. On top of that, we commonly either use protobuf or JSON for the payload. And we of course document the interface, so this system behaves in this way, and you can request this type of information, you will get it back in these formats and so on. Each of these services are deployable in isolation, so we can deploy one service and it will not affect any of the others. Again, this means that each team can decide on how they want to deploy. If it makes sense for a team to have continuous deployment, deploying many times a day, that's fine, they can do that. If it makes sense for another team or for another service to have a more controlled deployment procedure, they can do that. It's completely up to the team. This means that we also have quite a few of these services. We have, I don't know the exact number actually in production right now, but it's probably far more than 100 at this point. And I'm going to come back. This comes with consequences, of course, and we need to deal with having this amount of services in production. I'll come back a little bit to that. Our current tech stack when it comes to our run times is, well, I can give a short bit of history. When I started Spotify about 3 years ago, it was pretty much all Python. So pretty much all services except for 2, I think, was written in Python. We ran into a lot of scalability problems with Python. I don't know, do we have any Python fanboys in the house? That's one. Oh, quite a few. Great. So Python is a beautiful language on top of a shitty runtime. Scaling Python when you have basically a single thread running at any given point of time is really, really hard, it turns out. I think we've pretty much tried all the event-based systems in Python in production. We've even built our own. None of it really worked that well. So over time, we've now switched over to using Java instead. While Java might be the exact opposite of Python. It's pretty much a horrible language on top of a very good runtime. But it really, really works well in production. Today, I would say that user-facing, pretty much the large majority of our services are Java-based, and that has helped us tremendously when it comes to scalability. Yeah. That's a very good question. So we run on, we have only, at this point, we only have bare metal servers. We don't run on a cloud deployment. We run on, currently we're switching from Debian to Ubuntu for the operating system. And if you're familiar with Java, there's this tradition in the Java community to run these large app server, which are pretty much horrible. That's a large part of what I spent my life on earlier, running WebSphere or something like that. Spotify has opted for pretty much the opposite of that, and we don't run any app service at all. So each and every service boots up itself only based on the JVM, pretty much. When we need to have, for example, an HTTP interface, which we do at times, we use an embedded web server, embedded Jetty, usually. So did that answer your question? Good. Was there a question in the back? Nope. And like I said before, we have a minimal set of guidelines for teams when they choose their tech stack. So for example, when it comes to like storage engines, we don't want to operate 20 different storage engines and need to figure out how each of those should be backed up and how they should be managed. So we do have like a recommended set of technologies that you should use. So if you need to store stuff, we recommend that you use Cassandra or Postgres or some key value indexes that we use. But if your team really needs to do something else, I really need to have a persistent cache. Sure, you can use Redis for that if that's you really need to do that. Again, it's very much up to the team. So to illustrate how this works, let's try to follow how a request. This is very much simplified, but let's try to follow how a request how a request goes around in different services within Spotify backend. Of course, there are many different ways we do this, and this is the most simple one. It's a simple request reply initiated from the client. We do have other request patterns as well. For example, we do pub sub from our backend to our clients. We can do more advanced request reply where we send one request and get multiple replies back, if that makes sense. But this is sort of the basics. And this is also going to illustrate that we have a few different types of services. These are not very well defined, but I think it simplifies the discussion a little bit if you sort of look at this high level that there are a few different types. So starting, we have basically one or two of these that we call perimeter services. We have a few others that we actually call perimeter services, but this is the main one. And it's shortened AP, which is for access point. All the C's is trying to illustrate clients in that picture, and the dashed square is trying to illustrate a setup of the Spotify backend. This access point, basically, in our case, this is a little bit weird if you come from a traditional web application, but these clients try to maintain a persistent socket to this access point. And one access point will have something in the neighborhood of 30,000 clients or so connected at any given time. And these services, or this service, these services I should say, because we have a logical, a very much similar service as well, that I'm not going to go into today. This service has, its main objective is sort of to protect our backend from the internet, the evil internet. So it will do all the authentication stuff, it will do a lot of security stuff to make sure that it's only the correct clients that are allowed to connect to us, that we don't get DDoSed by clients and so on. So it does a lot of rate limiting, a lot of protection stuff to make sure that the backend is safe. This is a very hardened service. Our security team spends a lot of time working on this particular service, making sure that it's secure. And it will do routing to our backend. So when a client sends a request, this service or a companion service to this will look into that request, making sure it knows where to send that on. And replies will be routed back through this service as well. So then, if we look at this particular example, we're going to look at a search request. So the screenshot on the left is from our iOS clients, and when we do a search. So if we type in anything into the search box, it will send a request. This particular client will send a request to the access point. The access point again will route this and try to find the service to send this to. And in the case of search, this service is called the search view. And this means that we come to a second class of services, which are called aggregation services or view services. Basically, these services take requests and give responses which are very closely tied to the view that you see in the client. So these services aim to make client development easy, to make it easy to write a view in the client, in some of our clients. And the goal basically is that whatever makes sense for a client to send in the request and get back in the response, that's what this service serves. And these services are stateless, and they don't do anything by themselves usually. They might do some aggregation, of course, but they don't have any data, or they don't do much logic. That's our third class, which I'll come back to. But there was one point that we didn't actually discuss much when before this. So the access point actually needs to find this service. And again, we have many services, and I didn't mention this, but we deploy these on, there was a question about hardware. We don't have any like humongous hardware servers. We deploy on commodity servers, and we have plenty of them instead. That means that this search view will likely be on many servers, and the access points need to find where this particular service lives. And it might move over time and so on. We might scale it out, add additional nodes, we will scale it back, and so on. So the access point needs to find a way to do this. So we need to have some sort of service discovery mechanism. Spotify has, since its very start, been heavy users of DNS. We have a well-built out DNS infrastructure internally, and we use it for basically all of our service discovery. And we use something that is called SRV records. These are a relatively unknown part of DNS. The usual part of DNS that you use are just normal A records or maybe C names. SRV records are a bit different in that you don't send in a host name to an SRV record. Instead, you send in a service name. And back, you get a little bit more information than with an A record. So this is what this might look like. So if I do dig, which is just a simple command to look up, do DNS lookups, and I send this service name, which is a weirdly formatted string, which says Spotify search for finding the search service. HM is short for this Hermes protocol that I mentioned before. And then this is deployed into what we call a pod, basically a deployment unit of hardware that is called LON3. So it's in our London data center. And back you will get a list of nodes that represents this service. So basically this says in this case that we have two search services, or well, a list of search services, and you get the host names, and the number before the host name is the port where this service listens. And the numbers before that is the priority and weight. So you can actually use this for load balancing as well. We don't use it very much for load balancing, but it's part of the protocol, and you can do that if you like. Services can either dynamically, services instances, I should say, can either dynamically register themselves and say that I'm on this node running on this port, and DNS will reflect this, or they can be statically registered in our zone files. DNS helps with quite a lot of the getting a robust infrastructure for this, because one of the really good properties with DNS is that it has really good replication and caching. So we actually have a local DNS resolver on each and every server that we run. So every DNS lookup that we do towards localhost, and that will cache lookup results and make sure that they're available even if we can't reach our authoritative DNS servers. So this search view service that I showed on the previous slide, it will actually need to perform. Yeah, sorry. You mean when a service instance fails? Yeah. So that's a good question. So in the dynamic registration case, we will actually heartbeat, and that service instance will get deregistered automatically after, I think it's a minute or so. And in the static case, of course, we will need to go in to remove that manually. And in either case, actually, the client of this request needs to deal with service failure. So, I mean, even for that minute that it takes the dynamic registration to unregister, you need to deal with a service being unavailable. And different clients have different levels of advancement in this. So taking the access point service, for example, which is, like I said, a very hardened piece of our infrastructure, that has quite advanced blacklisting of upstream service nodes. So it will know that this node is down. I will probe that, but I won't send any request until a probe is successful. So we have a few mechanics like that. But usually we just make sure that we don't send any request to it. And the CRMQ protocol that we use, or the Hermes protocol that we use, actually make sure that this happens as well, because it will automatically not send stuff to a queue which is no longer up and running, and that queue is running in proc with the application. So if the node goes down or the application goes down, messages will automatically reflow to other instances. Yeah.
You said that you have extensive blacklists on your access point. Why blacklists and not whitelists?
You mean for broken service nodes? Well, I guess we have. Well, that depends on your definition of whitelist, I guess. But I guess we have both. I mean, whitelist is sort of the defined set of what the DNS server last replied that we should have. That's the known set of nodes that should be available. But then some of them might have failed unexpectedly, and then we have a blacklist for that. Should I repeat the questions, by the way? Can you hear them? Do you have any clue what I'm answering? I'll repeat them. There was a question up here somewhere. Can I come back to that? I have a slide on that in a little while. Is that? Yeah. So, and if I don't actually answer your question at that point, feel free to raise it again, and I'll try to answer it. Yep. So yeah. So this search view aggregation service, like I said, it doesn't actually do anything by itself apart from aggregating data from other services. So we need to have another step here. So we have a dedicated search service, and this is, like I said, this service knows our entire catalog, and it's based on Lucene, which you might be familiar with, and it's basically a big inverted index of this word appears on this track name or whatever. And the search view service will send down the search query that it got from the client to this search service, and back it will get a set of track identifiers or item identifiers. It might be a track or an album or an artist or a playlist or whatnot. But it will get back a list of identifiers for these. If you've seen You can see these Spotify URIs that you can copy-paste from our clients and share with friends or whatnot. That's actually the exact identifier that this service returns back. That might not be that helpful for the client because the end user probably don't want a list of completely opaque identifiers that only make sense to a Spotify developer pretty much. You want actual, like, decorated with metadata. You want the track name, you want the album cover or whatnot. The search service doesn't know about these things. It has this inverted index, but it doesn't actually know the complete track name. It doesn't know the cover image for this particular album. It doesn't know the portrait image for this artist or the tracks that is the top tracks for this artist and whatever we want to show in the result. Again, search does one thing and one thing well, and that is doing the search part. It doesn't do metadata decoration. It actually did at one point long ago in the Spotify history. Turns out that that's a lot of data, and trying to fit that into an already large search index doesn't make much sense. So instead, when the search view service gets this result back from the search service, it will send a second request to what we call the metadata service. And the metadata service can do exactly this. It can take a list of identifiers and decorate that with metadata. What doesn't show in this picture is that actually that metadata thing is actually also a set of services. It's also broken down into multiple services. But this is a little bit of a simplification. Both the search and the metadata service has data storage. So like I said, the search service uses Lucene, so it has a Lucene index that we will build offline on a separate set of services and then ship to our production services. You can argue that we should use Elasticsearch or something like that, and we might use that in the future. We might actually, well, we're actually using it already for some use cases. But one property that is very nice with having these sort of immutable indexes that we can ship to servers is that we can scale them very easily. I'll come back to this. And the same property is very much true for the metadata service. So that also has this static immutable index, and we can scale it easily. Of course, this is, I already said this, but this is vastly simplified. In reality, the search view service will send out many more requests than this to various backend services, trying to weigh in whatever you have stored in your playlists or whatever you have stored in your collection of music, or what friends you have. And maybe if you search and we return some Spotify users in that search result, maybe we should weigh up those that you follow and so on. So it makes a lot of different calls to our various backend services and then aggregates this into one response that gets sent back to the client. Again, taking into account that some of these systems might fail. So the playlist system, for example, is a big complicated beast and it might at some point fail. So then we make sure that in this search view service that if we time out that request to the playlist service, we make sure that we can still reply to the client with something that makes sense. I said early on that building these small services helps us scale, and that's very much true. And we have a constant need to scale out because we have a constant growth of users. Well, we've had so far at least, and hopefully that will continue. And having these commonly immutable independent services make that really easy. If you have a service like the metadata service, which is a small Java service with a immutable pre-built key value index, that means that these service instances are completely independent of each other, meaning we can scale that system out linearly. We can just add in, we can double up the number of services we run on, and we get the double number of requests that we can serve, making it trivial to scale out. And it's been immensely helpful for us. We also have the problem of geographical distribution. So our users, when Spotify started out, we basically had users in Western Europe, and we had a data center in London, we have a data center in Stockholm, and everything was fine. But of course, we've now launched in many other countries, in other places of the world. And that means that we need to move our data centers closer to the user. We need to have a data center which is as close to the user as we can financially possible have. This is a presentation by one of my computer science heroes, Grace Hopper, and what she illustrates is this close to 30 centimeter long piece of string, which represents the length that light can travel in 1 nanosecond. And what she's trying to illustrating, in her case, communicating with satellites, and there are many of these small pieces before we can get to the satellite. The same is certainly true in between the Spotify data centers and our users. And of course, in user experience, the latency is a big has big impact on how users feel about an application. And one thing about having these independent small services that are really built for being distributed means that we can deploy these in multiple different data centers. So today we have 4 data centers around the world, and we might have more in the futures. One pattern that we've seen works very well for us, and we've tried a few different other ways of doing it, is that the actual services that we have, the Java services that we have, don't take into account that there are other data centers around the world. They just know about serving their particular requests. But of course, then we need to actually distribute stuff. So if a user creates a playlist in our Ashburn data center on the US East Coast, we want that to be available for a user in Europe, for example. And the way we usually do this is by having a replicated storage. So we're heavy users of Apache Cassandra, which is a beautifully working storage. So basically, when you create this playlist in Ashburn, it will write that down to Cassandra. The service have no idea that there are other data centers. And Cassandra will replicate this for us, and it will appear in for a service instance in the London data center normally within milliseconds. It was actually a very poor example because our playlist system is a bit particular in that it's actually only deployed in our London data center. That might change. So we end up with this. I don't know if this is this even readable. It's the same picture as before, but we have multiple copies of it, and each of these are relatively unaware of each other. Again, we might have replication for storage. We might even have some other replication for logs or whatnot. But basically, these services are independent of each other. This also means that this is a good way for us to have something that is similar to, for example, AWS availability zones. So if we have a problem in one of these data centers, and we do because of network failures or whatnot, we can take down that entire site and move users over to a different site without the user actually noticing. And we do this every now and then. We did it, I think it was 2 weeks ago or so. We had a lot of problems when there was an Atlantic fiber cable that was injured from one of our backbone providers, and we had a large problem replicating some of the data to our San Jose data center. And then we could just take that down, make sure that the users connect to some other data center that works better for the moment, fix our problem, and then let users in again. Yep. So that's yes, I should repeat the question. Sorry. So what's our strategy when it comes to merge conflicts in our storage? That was about it. So Cassandra has a very simple and stupid way of dealing with it because it just uses the last write wins, given some timestamp. There are plenty of discussions on the internet about this if you want to read into the details. That works okay-ish, but you can model your data around that. So taking, for example, our playlist system into account again, and this is one of the things that makes the playlist system quite complicated, is that for playlists, we also want users to be able to edit playlists while they're offline. And we even want them to be able to do this on multiple devices. Because you can have a collaborative playlist, for example, and in theory, hundreds of users can edit this at any given point of time, and some of them can be offline. And when they get get online again, we want their changes merged into the playlist. So we have sort of a Git-like system, or a distributed version control system in this. And to get back to your question, that means that we can model our data structure for playlist in a way that makes it easy, or actually in that case guarantees that we can merge everything into the playlist. It might mean that the order of tracks gets weird because of merge failures, but we will always get all the changes in. There's plenty of academic papers around algorithms to do this. There are like CRDTs and data structures like that. And we do that for other cases as well. So for example, if you store a set in Cassandra, you can make some guarantees around how that merges in a proper way. But if you have there are some particular ones that are really hard to deal with, and maybe you need to design around that. Did that answer your question? It was, yeah. So the question was, how do you move users to another data center in case of failures? This happens in two different ways, well, to simplify things a little bit. I didn't go into this, but before the client can actually connect to an access point, it will query a different service to get an address to an access point. We actually did and still support doing this in the exact same way that we do service discovery in the backend. So there is a public SRV lookup that you can do towards a public domain where you can find the address to these access points. But we, for various reasons, mostly doing geo-IP localization of people using DNS is really hard because you don't actually get the location of the user, you get the location of their name server, which might or might not be that useful. So today we use a different service. That service can take into account, well, or rather we can configure that to make sure that any new connection will go to this particular data center. We will basically blacklist saying, right now the San Jose data center is down. Don't send any user to that. Should send those users to this data center instead, or these data centers if one of them can't handle the load or so. So that's one part of it, sort of the service discovery of access points. The other part is actually actively moving users which are already connected. So like I said, users maintain a persistent socket to an access point, and we want to move that to a different site. And then we actually have a command in our client server protocol that can tell a client to reconnect. So we can go into one of these access points, send a command to it saying, please disconnect all your users. The access point will send this command to all its users saying, please reconnect. That client will go do a new service discovery request for access points, getting redirected to a different data center. And all of this is completely invisible to the user. So you won't notice, the client won't say that it's reconnected or anything. That just happens under the hood. And we actually do this automatically for these persistent connections. So if you lose that because your firewall shuts down your connection, or well, you just lose network for a second, the client will actually automatically reconnect under the hood as well. Yeah.
You said that Netflix were trying to get as close to the customer as possible by using physical data centers. At what point do you think you'll start to try and use them?
So the question was, to summarize it, will it at some point make sense for us to use the cloud to get closer to the user? And I think the answer is yes. But today we only use physical hardware in co-located data centers. But, well, we get the slightly longer reasoning about this. We get users that are further and further away from our data centers, and they are in countries which are not as significant as the US, for example. So it might not be financially viable for us to build a data center in many different parts of Asia or in like Australia. We're not that big, so then it might make sense to use the cloud instead, but we're currently not. All right, so I said there was some cons to this, and of course there is. So building these microservices, or whatever you want to call them, is certainly not a silver bullet, and it comes with a bunch of consequences, negative consequences. One of them is that you can get fairly complicated failure modes. And I'm going to go through a few of them. These are certainly not all of them. A very common one is that you can get cascading failures. I mentioned multiple times this service that does playlist subscriber counts. If that fails and a lot of other services depends on that returning data, they will fail. There might be a third layer of services depending on that second layer, they will fail and so on. We've done this many times. We're really, really good at screwing up. So we've done this many times, and in particular, we have a service, I mentioned it shortly before, there's called a user service, and it basically keeps track of all users, usernames, authentication details, and so on. That's a service that previously, at least, many other services were dependent on, and still are. And at some point in time, maybe 2 years ago, so it had huge scalability issues and was basically down more than it was up for some time. Again, having many services depend on it meant that many services would fail when that user service failed. And we actually worked quite hard to work around that and find other ways to decouple these so that services weren't completely dependent on the user service being available at all points, at all times. So cascading failures can be very annoying and have great effects. Like I mentioned before, one of the benefits of having small services is that you limit your blast radius. But if you have cascading failures, again, you get larger portions of the functionality that gets affected by a failure. You don't want that. And yeah, and I already mentioned that we can even have larger scale, like site failures, and then we really want to isolate so one site doesn't actually take down a second site. At some points we have problems with actually moving users over because we don't have sufficient capacity in our data centers to move an entire site to a different site. So we might need to spread them out, meaning that the users will have a higher latency towards our data centers. And things will fail in general. So if we have something like 5,500 or 6,000 servers or so, I think, and there will always be a lot of them being broken in various ways. Disks being broken, or BBUs being broken, or whatnot. And you really need to design your entire architecture and assume that that's the case. Don't assume that your hardware is working and deploy on a single server. We will never deploy our services on a single server in a data center. We have usually at least three servers that we deploy each service on. That means that we have a fairly low usage of our hardware, but it also means that we have a great redundancy. And we can certainly do more with virtualization in this area, and we're probably going to do that, but at this point we're doing very little. And basically, when you build a system, assume that this is going to be a distributed system. Even if currently it looks like this will fit on one server, I can have a simple failover scheme where I basically start up a different instance when this first instance fails. But I argue, don't build services in that way. Instead, build them so that they're distributed by default. And that means that you have this nice property where you can scale it out. So the question was, do we deploy any chaos monkeys? Yes, we do at limited, well, not in the same structured way that Netflix does, for example. They're very famous for doing this. But yeah, we certainly do similar things. We do have some chaos monkeys that we can inject into our infrastructure. We have small scale chaos monkeys that we can actually run in our services to respond in various different ways. We do complete site failure tests, for example, where we take down an entire site and make sure the failovers work as we expect. So we have some of that, not at the scale that Netflix does, though. And we should probably do more of it, I would argue. So this is one of the things that were quite weird to me when I started Spotify. So the way, and this was also obviously weird to a lot of big part of Spotify. So one of the things that we did previously was that we were really afraid to drop requests. So when we got overloaded, we instead had queues in our systems to make sure that we kept every request around and would respond to the client to this request. This made us have huge scalability issues when a system would fail. So imagine again the search view service and the search service being really, really slow. The search view service will just queue up requests. In the worst case, you have an unbounded queue, so you will just queue up requests until your finite memory runs out, and then you're sort of screwed. But even if you have and we didn't well, we had unbounded queues, but we also had really large queues where we would queue up like hundreds of thousands of messages. Imagine this search service, which normally responds within a few milliseconds, all of a sudden gets slow for whatever reason and will only respond, well, let's say it responds once a second. And you have this queue of 10,000 messages. That means that you won't respond to these within 3 hours. The user that made this search is probably not around when you send that reply. So instead, what we've started doing is to have really shallow queues. Instead of having hundreds of thousands of items in a queue, we might have 30. And instead, drop stuff when we need, and make sure that clients deal with this properly. So we will time out in the client, tell the user, sorry, this failed, try again, or make a exponential back-off retry for this request from the client and so on, instead of trying to make sure that we respond to everything. Of course, this depends heavily on your domain. If you're my bank, I don't want you to lose requests, but we're a music player. We can mostly drop requests. That helps us with our scalability. And this might seem easy when it comes to queues, but you should consider that stuff like thread pools and connection pools are just queues in hiding. And if you have a huge thread pool, that will just serve as a queue, because you won't actually get that much done. If you have a thread pool of 10,000 threads, you might not actually have all of them running on your 32-core server. So that's just a queue of stuff that you want to happen in the future. So again, make sure you use reasonably sized thread pools and connection pools as well. Back to your question on deployment. So when you have 6,000 servers, and I'm running out of time. When you have 6,000 servers and you have a lot of services, you can't deal with them manually. You can't deploy stuff manually. You can't configure servers manually. So you need to automate pretty much all of this. And we're now at a point where pretty much all of this is automated. So hardware provisioning and cloud provisioning for our testing stuff is automated. We just run a command and get a server back, or enter a request for a server and have that served for us. Same with deployment. So we package all our services into some form of package. At this point, we actually use 3 different types, which is a bit weird. We use Debian packages. We use Java jar files for some stuff. And we use Docker containers for some stuff. And the reason why we have all of these 3 is that they make sense. They make sense for different purposes. We might, over time, simplify this into using fewer options, but at this point we use these 3 different for various reasons. We make sure that all of these packages gets deployed deployed into repositories and is available from all services. We have a complete history so we can roll back and forth. And we automate the deployment of these packages. Usually, well, we have different tools for that, but the common way is that we use Puppet, which is a configuration management system with fanboys. And we do all our configuration using Puppet as well. So a server we have no manual configuration of servers. They're completely automated in how we configure them and deploy them, which is hugely helpful. Same thing with monitoring. When you have thousands of servers and many service instances, you need to have very good monitoring. Our monitoring is getting better. It's been terrible, and it's now in a shape where it's actually back to being useful again, but we have a fairly long way to walk, I would say. We're heavy users of Reman for alerting. So basically, our services and servers will send out events into an event infrastructure that either puts those events into a graphing system for the classical graphs that you would get out of Graphite or whatever you're using, and it goes into an alerting system which wakes us up when we're on call, saying that this server now has too many 503 responses or whatever. And this is something that, again, needs to be really well functioning if you have a lot of servers. Last slide. So is this useful even if you're not at a scale of Spotify or for any service? I would argue that for the stuff that I worked on previously, which was like normal business applications within enterprises, I would say that, yeah, it's very, very useful. And I would actually argue that everyone should consider this when you architecture a new system. Does this make sense for us? And I think that in many cases it will turn out that it would make sense, and it would greatly simplify operating your system. So have a look at this for your future work, and read into. There's plenty of materials online on this now that it's gotten a big hype, and you can start with the Martin Fowler article that I posted earlier, and there's tons of stuff around that you can read up on. It's well worth considering. Any further questions? I have 3 minutes. Yeah. Good question. We just had a discussion before. That can be really complicated, actually, and we certainly don't have the best infrastructure for that. For example, we currently don't have a solution for tracing requests that go through our infrastructure. And that's something that I think that we probably should invest in, but we don't at this point. So it can be hard at times, but that's also compensated by it being greatly simplified at the service level. So I can really easily argue about what happened to a request in this particular service. That part is very simple, and we can hook up debuggers, we can hook up JMX or whatever to find out what a particular service does. But we don't have a good way of sort of looking back and having a good understanding of the entire history of a request. And I think you will get some more of that in one of the talks later on. Yeah, there was someone, yeah. Good question. Yes, so what's the incentive for Spotify to use CRMQ instead of HTTP? This has some history, and I have 2 minutes, so I'll keep it very brief. We had a lot of problem with HTTP. And a lot of that problem, I would argue, boils down to two different aspects. One is, this was at the time when we were heavy Python users, and Python HTTP clients suck ass, or at least did at that point in time. So that's one of the problems. The other problem is comes back to this thing I said about drop-in requests. So basically, one of the problems that you have with HTTP is that you have a connection pool in your service, and that's a hidden queue. And when that service gets slow, you will typically see that clients will use more connections in their connection pools, meaning that the service will get even more connections open. And if you're really slow and having a bad time as a service, getting more connections and more requests in parallel usually doesn't help. So we got these escalating failure modes where having something go slow meant that it would go even slower and even slower and even slower and grind to halt. And CRMQ or queuing systems in general, instead of having this connection pool, you have one connection and you multiplex messages over that. So it makes that failure scenario sort of go away, which is quite nice, actually. That said, it's a bit weird using a protocol which is not HTTP, because everyone is using HTTP. So it comes with a set of costs. You need to develop tools around this and so on that is perfectly available for HTTP. So it's not free. Yeah, I guess one more question, if there's anyone. Yep. What do you do for integration testing in between your services? That's embarrassing. We basically don't do anything, and we have a poorly functioning test environment. I would love for us to get better at that, but at this point we're actually in a pretty poor state. The way we usually do it is that we set up a test service instance towards our production and run tests towards that. But we're at a pretty poor state, I would say. We do a lot of test automation from our clients, though. So actually automate our clients and make them run requests towards our backend. And that certainly helps, but it's not a perfect solution for integration testing within the backend. So we should do that far better. All right? Out of time? Cool. Thank you very much.